This is problem 29 from chapter 18. The 10-pound sphere starts from rest when theta is equal to 0 degrees and rolls without slipping down the cylindrical surface, which has a radius of 10 feet. Determine the speed of the sphere's center of mass at the instant when theta is equal to 45 degrees. So in this problem we have rolling without slipping, which means that we have a force of static friction instead of a force of kinetic friction, and the force of static friction does no work. We also have a normal force which does no work. So the only force that we have that does do work is the force of gravity, and for that we will use gravitational potential energy. So I want to know the change in gravitational potential energy, so I have to figure out how the height of the ball is changing. This is for the initial height of the ball, and we're going to measure from the ground. Since the radius of the surface here is 10 feet and the radius of the ball is 5 feet, this is 10.5 feet. And then if this angle is 45 degrees, then this angle is also 45 degrees. From here to here, that's the radius of the surface plus the radius of the ball, so that's 10.5 feet, and I want the sine component of that. So that's 10.5 times cosine of 45 degrees, which is 10.5 times 0.7071. So this distance, which is the distance that I'm looking for, is the difference between, well, it's the difference between what I have here and what I have here. So that's 10.5 minus 10.5 times 0.7071. And because I'm ending at a lower height, the change in gravitational potential energy is going to be negative. So change in gravitational potential energy is m times g, which is 10 pounds, times the change in height, which is negative. And it's 10.5 minus 10.5 times 0.7071. That gives me negative 30.75. And the sphere started from rest, so T1 is equal to 0. For T2, I have to include the translational kinetic energy and the rotational kinetic energy. So I have T2 is equal to 1/2 times the mass times Vg squared plus 1/2 times the moment of inertia about the mass center times omega squared. Since we have rolling without slipping, the velocity of the mass center is equal to the radius of the sphere, which is 0.5 times omega. Since I'm looking for the velocity of the mass center, I can say omega is equal to the velocity of the mass center divided by 0.5, and then put that in here. Then I also need to know the moment of inertia for the sphere, so I go to the back of the book, and for the moment of inertia for the sphere, I have 2.5 times m times r squared, 2/5 times the mass times r squared. So I have 1/2 times the mass times Vg squared plus 1/2 times 2/5 times m times the radius of this sphere, which is 0.5 squared, times omega squared, and omega is V sub g over 0.5. The 2's cancel out here. This is the radius squared. In the denominator I have the radius, and that's being squared also. So this is 1/2 mvg squared plus 1/5 mvg squared. 1/2 plus 1/5 is 7/10. So this is 7/10 times the mass times the speed squared. And then I can go back to my work energy conservation law. This is equation 1818, where the work done by non-conservative forces is 0, then bring the V1 over to the other side. So we can use this equation now and plug things in. T1 is equal to 0. T2 is 7/10 times the mass. M times G is 10 pounds. So the mass is 10 divided by 32.2 times Bg squared minus the change in, well, plus the change in gravitational potential energy, which is negative, so minus 30.75. Then we can solve for the speed, and we get 11.9 feet per second, and that is our solution for problem 29.